All right, today we're going to pull back the curtain on a really powerful statistical tool, one that's absolutely crucial in the world of health and medicine. It's called ANOVA, and it's basically the secret weapon researchers use to find a real, life-saving signal in a whole sea of confusing data. So let's make this real with a classic scenario, right? Imagine researchers have developed three brand new treatments for a disease. They run the trials, they get the results, and now they face the big question. How do they figure out which one, if any, is actually the best? You'd think it would be simple, but statistically, oh, it's a total minefield. And this gets us to what a lot of people call the three-way problem. See, when you're just comparing two things, like a new drug against a placebo, the math is pretty straightforward. But the moment you add a third option, or a fourth, or a fifth, you introduce this hidden statistical challenge that can really easily lead you to the wrong conclusion. So, what's the first thing you'd think to do? Well, this is where we run straight into a really common statistical pitfall. We'll call it the comparison trap. It's the approach that seems totally logical, but believe me, it's actually deeply flawed. I mean, the obvious first step is just to compare them two at a time, isn't it? You'd run one test for treatment A versus treatment B, then another for B versus C, and a final one for A versus C. Simple. But here's the catch. Every single time you run a statistical test, you're taking a little gamble, a small risk. And those little risks, they start to add up fast. So that risk? Statisticians have a name for it, a type 1 error. But you can just think of it as a false positive. It's basically the statistical version of a smoke alarm going off when there's no fire. You end up concluding that, hey, there's a real difference between these treatments, when actually, there isn't one at all. It was just random luck. And this isn't just some abstract idea. A false positive can lead to millions of dollars wasted on a useless drug. Or even worse, it could give patients and their families false hope. And this is where it gets kind of crazy. In science, we usually accept a 5% risk of a false positive for any single test. That's pretty standard. But when you run three separate tests like we just talked about, your chance of getting at least one false positive skyrockets from 5% all the way up to about 14%. You've almost tripled your odds of being tricked by randomness. That right there is the comparison trap, and it's exactly why we need a smarter, safer way to do this. All right, so how do we get out of this mess? We need a tool that can look at all three treatments at the same time without jacking up our error rate. And that brings us to the really elegant solution, which is all about understanding the difference between a real signal and all the background noise. And this is where our hero, analysis of variance, or ANOVA for short, steps onto the stage. Just like the name says, it works by analyzing the variance in the data, how spread out all the results are. It gives us one single powerful test to see if there's a real significant difference somewhere among all of our groups, all while keeping that false alarm rate at a safe level. So what ANOVA does is actually kind of genius. It takes all that messy data and splits it into two parts. The first part is what we can call the signal. This is the between-group variance. Basically, it asks, how different is the average result for treatment A compared to the average for treatment B and treatment C? If one drug is truly working better, we would expect its average to be pretty different from the others. That's the signal we're hoping to find. And then, on the other side, you've got the noise. This is the within-group variance. It's all the natural, random variation you see among people inside the same group. You know how not everyone responds to medicine the exact same way? That's due to genetics, lifestyle, a million different things. All that randomness creates noise that can make it really hard to hear the true signal of the treatment effect. And here is the magic trick. ANOVA boils all of this down to one beautiful, simple number, the F statistic. Now, don't get scared by the name. Just think about the concept. All it is really is a ratio. You take the signal and you divide it by the noise. So if the variation between the groups is way bigger than the random variation within them, you get a large F statistic. And that tells you your signal is loud and clear, and there's probably a real difference between your treatments. It's that simple. Okay, so that's the core idea, right? Signal versus noise. But what makes ANOVA so powerful, so useful in the real world, is how flexible it is. It can handle way more than just one simple comparison. Let's see how it can get even more sophisticated. Let's start with the most straightforward version, the one-way ANOVA. You use this when you have one single factor that defines your groups. So for instance, in this table, researchers are looking at platelet counts in patients who have different levels of gangrene severity from group 0 to group 3. A one-way ANOVA is the perfect tool to tell them if there's a statistically significant difference in platelet levels somewhere across those 4 groups. That could be a huge clue about how the disease works. But what happens when things get more complicated? What if you think 2 different things might be at play? Well, that's where a two-way ANOVA comes in. It lets you look at 2 factors at the same time. For example, is treatment A different from treatment B? And does a patient's gender affect the outcome? A two-way ANOVA can answer both questions. And this is the really cool part. It can even tell you if there's an interaction. Maybe treatment A works great for men, but treatment B is actually better for women. That's a game-changing insight you would totally miss with a simpler test. Okay, so you did it. You ran your ANOVA, you got a big F statistic, and the computer spits out a significant result. Awesome. But what now? What does that actually tell you? This brings us to the last and maybe most important step, actually interpreting what you found. This is probably the single most important thing to remember about ANOVA. A significant result is that smoke alarm we talked about. It's blaring, telling you there's a fire somewhere in the building, but it doesn't tell you which room. It confirms that a real difference exists somewhere among your groups, but it doesn't pinpoint which specific groups are different from each other. Right, so just knowing there's a difference somewhere isn't really the answer we need, is it? We're right back to our original problem. Which treatment is the best one? Is C way better than A and B, or are A and B about the same, but both of them are better than C? The ANOVA test by itself can't give you that answer. So to find out exactly which room the fire is in, researchers use something called post hoc tests. It's a fancy term that just means after this. And this is the key that brings it all full circle. These follow-up tests go back and do those one-on-one comparisons, A vs B, B versus C, and A versus C. But they use special adjustments to fix that comparison trap from the beginning, keeping your overall false alarm rate at that safe 5%. It's how you can find the signal and then find out exactly where it's coming from without getting fooled by noise. So now you know the secret. The next time you see a news story or read a study that's comparing a bunch of new treatments, you'll know what's going on behind the scenes. You can ask the smart question, are they really seeing a true signal, or are they just getting lost in the statistical noise?